Welcome back. We're jumping straight into the curriculum of an engineering workshop today, diving into a set of source materials that define how electrical engineers approach design, starting with the absolute basics.
That's right. And this deep dive is built around a really fundamental question, a dual framework for every single component. What is it? And then why do you need it?
The property versus the purpose.
Exactly. We're going to get granular first, focusing on, well, maybe the most ubiquitous component there is, the resistor. But the true mission here is to bridge that gap between the microscopic technical specs, things like a parts per million drift, and see how they scale up.
How they become these large, socially relevant engineering projects.
Right. It's that journey from the theoretical what to the practical why.
Okay, so let's start with that analytical framework. When you're looking at any electronic component, you start with the what.
The what, yes. So properties, physical characteristics, shape, size, electrical value, all of that.
And then you have to immediately ask the why.
Immediately. What's its function, its application? I mean, what systemic problem is it actually solving? The sources we have use really simple components to lock this mindset in.
Like a piece of wire.
Exactly. Take a wire. Its primary, what's its conductivity? But, and this is interesting, the sources pointed out that high conductivity isn't always the goal. Sometimes you might want a bad conductor.
Why would you want that?
Well, because that inefficiency generates heat.
Yeah.
And sometimes heat is the desired output.
Okay, that makes sense. So for a normal wire, the why is just interconnection, making the circuit whole. But a fuse is different.
Very different. The what of a fuse is defined by its current rating and maybe if it's a slow blow or a fast blow type.
But the why, the really critical why, is circuit protection.
It's circuit protection and, I'd argue more importantly, malfunction isolation. It ensures that if one part of your system fails catastrophically, the fuse is that designated weak point.
It sacrifices itself to save everything else.
Precisely. And that same rigor of analysis, what properties, why function, that now gets applied to the cornerstone of electronics, the resistor.
Defining a resistor seems easy on the surface. It just constricts current flow.
That's the textbook definition. But the real engineering lies in the practical specifications that go way beyond Ohm's law and into the physical world. The sources laid out 5 essential specs that a designer has to master.
Okay, what's first?
We start with its value, and then the critical specification of power dissipation. In introductory theory, we often just ignore this. We assume the resistor can handle any load.
But the workshop really stressed this is a major, important concern in any real-world circuit.
It is. And here's where the rubber meets the road. If the theory ignores it, what happens in practice? I mean, does choosing the wrong wattage just mean poor performance?
I'm guessing it's worse than that.
Much worse.
Yeah.
If that resistor can't dissipate the power being forced through it, say a tiny quarter-watt resistor trying to handle 5 watts, that excess energy just turns to heat. Endofetal.
So you don't just get poor performance.
You get thermal runaway, you get smoke, you get a fire hazard. Designers have to select the physical size and wattage rating just to ensure safety, which is why, a 10-watt resistor can be physically enormous compared to a tiny 0.1-watt one.
All right, spec number 2 is tolerance. This is how much variation you get from the advertised value.
Yes, and we often see standard 5% resistors. But modern manufacturing has made just huge strides here.
Absolutely. The ability to reliably make 1% or even a hyper-precise 0.1% tolerance resistors, that reflects massive improvements in the process.
Decades ago, 10% was fine. It was acceptable. Now, if you need critical precision in, say, a measurement device, you can count on those really tightly controlled specs.
Okay, now for the spec that you said really separates the hobbyist from the professional designer, the temperature coefficient, TC.
This is a major differentiator. TC measures how much the resistor's value changes as the ambient temperature changes.
And the ideal TC is 0, right? No change whatsoever.
The ideal is 0, but that's physically impossible. So we have to measure the deviation in parts per million per degree centigrade, or ppm per degree C.
Let's do the math on that because this is where the implications really hit home. So take a 1 megaohm resistor with, let's say, a pretty good 10 ppm degree CC.
Okay.
What happens if the operating temperature varies by 100 degrees Celsius, which is pretty common in industrial settings?
Right. So the variation works out to 10 ppm of 1 May multiplied by that 100 degrees of variation. It comes out to 1 kilom of drift.
Now, you might initially think, wait, a 1K drift out of a 1 May, that's only 0.1%. It sounds trivial. Why would that specifically ruin your design?
That's the perfect question. Why is 0.1% a deal breaker?
So why is it?
Because in so many precision analog applications, especially in sensing or metrology, that resistor isn't just limiting current, it's defining a reference voltage.
And every other measurement is made against that reference.
Exactly. So if that reference voltage starts to drift by even 0.1% across temperature, your sensor readings become unreliable, your calibration fails, and, well, the entire system loses its intended function.
So that's why paying for a 5 ppm resistor instead of a 100 ppm resistor is so critical for reliability.
It's everything.
Okay, so beyond the electrical properties, what also includes packaging types and coating, we have the traditional leaded resistors and then surface mount devices, or SMD.
Right. For leaded resistors, that classic old color band code is still standard. 4 bands for 5% tolerance, but you need 5 bands if you're moving to 1% or better.
Because you need the extra significant figures for the value.
Precisely. And for the tiny S&D components, the value is just printed directly with the code. Like 103 means 10, followed by 3 zeros, so 10 key.
And when you're sourcing an SMD resistor, the physical size is specified by a 4-digit number, like 1206 or 0402. How do engineers read that?
Those numbers specify the size in hundredths of an inch. A 1206 part is 12 hundredths of an inch long by 6 hundredths of an inch wide.
Which is absolutely minuscule.
Tiny. You need forceps, or more likely, automated pick-and-place machines. And this size factor is incredibly crucial because when you scale up manufacturing, switching from a 1206 to an 0402 means you can pack 4 times as many components onto the same circuit board space.
And that drastically reduces your product cost and footprint.
Massively.
Yeah.
And finally, there's this fundamental connection to sensors. If a manufacturer deliberately enhances a resistor's temperature coefficient, well, it stops being a standard resistor.
It becomes a thermistor, a dedicated temperature sensor.
A thermistor, exactly. Either positive TC or negative TC. The resistor really is the foundation for so much else.
Which brings us perfectly into the why of resistors, starting with their simplest purpose, current restriction.
Yes. The classic practical example from the sources is always connecting an LED to a standard 5-volt USB source.
You can't just connect the two directly.
You can't. The V sub F, or forward voltage, which is basically the minimum voltage needed to turn that light on, it varies drastically depending on the color. A red LED might turn on at 1.6 volts.
But a blue or a violet one might need 3.3 volts.
Right. So if you apply the full 5 volts directly, that LED is going to burn out instantly.
So we need a series resistor to drop that excess voltage. The math is pretty simple, just Ohm's law. R equals the source voltage minus the LED voltage divided by the current you want.
And the workshop used specific values, 5V source, a 1.7V red LED, and they wanted a target current of 10 milliamps.
And that calculation gives you 330 ohms.
It does. Now, the next question is, how do you know you can actually buy a 330 ohm resistor off the shelf? And that brings us to component standardization.
Right, because we're conditioned to think in sequences like 1, 2, 5, 10. You see it in money or on an oscilloscope, but that's not how resistor values work.
No, it's far more mathematically elegant. The standardization is all driven by minimizing inventory while guaranteeing every possible resistance value is available once you account for tolerance. It's based on the E-series.
The elegance here is just astonishing. Explain the core logic.
Okay, so imagine you're designing a fence. You want the fence posts spaced so that the width of the first post, plus its allowed wiggle room, its tolerance, perfectly meets the starting edge of the next post's tolerance range.
So there are no gaps.
No gaps. That's the E-series. Component values are selected so the tolerance range for one value coincides perfectly with the tolerance range of the next. It ensures there are 0 gaps in available resistance while using the minimum number of parts.
So if you're working with standard 5% tolerance, you use the E24 series.
Which gives you 24 unique values per decade. So from 10 to 100 ohms, you'll have 24 distinct options.
And if you need better precision, like 1% tolerance, you move to the E96 series.
Which gives you 96 unique, specific values per decade. It just goes to show that every single choice, down to the exact ohm value, is governed by this rigorous engineering system built for precision and manufacturing efficiency.
Okay, moving beyond just simple current limiting, resistors are absolutely essential for creating more complex circuit functions, like a voltage divider.
Yes, which is key for providing the precise bias point that active components, like transistors, need to operate correctly.
They're also critical for signal integrity, using pull-up and pull-down resistors in microcontroller circuits.
This is a big one. When an input pin is floating, not actively connected to a voltage, it basically acts like a tiny little dangling antenna.
And it picks up random electrical noise, causing all sorts of chaos.
Exactly. Unpredictable logic states. The pull-up or pull-down resistor acts like a tether. It weakly connects that input to either the power rail or to ground, ensuring the pin is always in a known state.
Without them, you just get system crashes.
You do. And resistors are also used to provide gain in amplifiers. And when you pair them with capacitors, they become the building blocks of timing elements like oscillators.
Where the R and C values determine the output frequency.
Right. So we spent all this time mastering the rigorous technical foundation, the PPM, the E-series, why you need pull-ups. Now we make the grand transition, applying those microscopic details to solve big real-world problems.
This is where the workshop challenged the students to move from theory to 5 ambitious engineering projects. And this is where all those constraints of size, like the 0402 SMD, and cost, choosing E24 over E96, really dictate whether a project is even feasible.
Exactly. Project 1 was the interactive map of India.
And the technical challenge here was way more than just lighting up some LEDs.
The goal was a large human-scale, hands-on map for schools. It needed about 40 switches for all the states and territories. The real challenge was the interfacing. When a state is selected, the system has to instantly display live data feeds.
Like what?
Things like ethnicity, male-female ratio, current weather, even real-time air quality index or AQI. This requires really careful filtering of input signals and distributing power, so choosing the right current-limiting resistors is crucial.
Okay, project 2, the photo light box. This was for improving product photography.
Good lighting is the first thing you need for a good product shot. But the critical technical requirement here was adjustable color temperature.
Meaning you can change the light from warm to cool.
Precisely. The student had to design a circuit to blend different types of LEDs. Warm white, which has more red, and cool white, which has more blue, so the user could finely tune the mood of their photograph. That means very precise voltage dividers to control the brightness of the different LED strips.
I really liked the educational fun behind Project 3, the intergalactic weight scale.
It's a genius concept for teaching physics. You hack a standard weighing scale, which is basically just a sensitive load cell, and you reprogram the output. The system multiplies your weight by the G value of another celestial body.
Like Mars or Neptune.
Right, and it displays what you would hypothetically weigh there. The stability of that analog signal conditioning circuit, which is built on op-amps that use resistors to set their gain, is paramount. If those resistors have a high TC, your weight reading will drift as the device heats up.
Then there was a sports application, the table tennis response improver. This is about making high-level training affordable.
Right. High-end training gear can cost thousands of dollars, way out of reach for most people. This low-cost system divides the table into sections with sensing pads that light up in a random sequence.
And the player has to quickly touch and turn them off to improve their response time.
Exactly. And because it involves all those sensing inputs, the use of stable pull-down resistors to prevent those floating inputs we talked about is absolutely non-negotiable.
And finally, a key utility project for industry. The mains fluctuation pattern analyzer, a classic IoT challenge.
This is a device for power companies or businesses that have chronic intermittent power issues. It sits on the power line, and it characterizes the specific pattern of power quality at that site over time.
So it doesn't just record that the power went out?
No, it notes the duration and intensity of sags and surges. That data is then used to figure out exactly what kind of power backup system is needed. And for a device like this, the measurement circuitry has to have the highest possible stability.
Meaning the designer must use high-precision, low-temperature coefficient resistors.
They have to make sure the measured voltage is accurate, regardless of temperature changes inside the box.
What a journey. I mean, we started with the excruciating detail of a resistor's PPM value, the need for a tiny 0402 part, and the math behind the E-series. And now we've connected that all the way to professional-grade tools like that mains analyzer.
And that synthesis is the whole point. You covered the foundational physics, why tolerance overlaps, why PPM matters, and then you transition seamlessly into applied design. The professor who delivered the workshop, he summarized this whole idea with a simple but profound life rule.
Right, the rule was do what you love, but it was the addendum that really provided the challenge.
That's it. Then there's an addendum to rule number 1, love what you do.
The implication being that you may not initially love the struggle of calculating PCAP's drift.
Of course not. Or designing complex voltage dividers.
Yeah.
But if you apply yourself, if you put in the rigor to master those microscopic technical details, you gain a mastery that transforms a necessary task into a lifelong pursuit.
And that challenges you, the learner, to move beyond just a passive interest. I mean, consider that painstaking effort it takes to make sure that one Kate drift in a sensing circuit doesn't ruin the entire project. That perseverance, focused on the technical what, is exactly what enables you to achieve a truly impactful why.